So now let's look at another example and theorem that we have for cylindrical shells. So the theorem deals with two different functions, f and g. So just like with the washers method, we had two different functions, we're going to be able to do that with cylindrical shells as well. So in this case, if f and g are continuous on the closed interval, where a is greater than or equal to 0, and f is greater than or equal to g on that closed interval, and the region that you get has all those things bounded and rotated about the y-axis. I left that part out. Then the volume is going to be 2 pi times the definite integral from a to b of x times the difference of the functions f of x minus g of x with respect to x. And I'm going to give you an example to kind of show you why that's the case. But basically we're going to be bounding the region bounded between f and g on the top and bottom side, on the left by x equals a and on the right by x equals b, and rotating around the y-axis. That's the part that I left out here. So let's look at an example. And I changed up, it's the same example we had last time, except instead of calling f of x equals the square root of x, I'm calling this g of x is the square root of x because it's going to end up being the one on the bottom. So I wanted it to match the theorem here. But basically we're still going on 0 to 16 for the x values, and we're bounded by the lines y equals 4 now, so we're up at 4 here for the height, which we were before, right? But instead of y equals 4, I could actually call that f of x equals 4. So that's actually the top one. The y-axis, so we're bounded on the left side by the y-axis and our function. So we're bounded on the top side, the left side, and by our function. So instead of shading underneath the curve, we're shading over the top of the curve between that and the height y equals 4. And then I drew the mirror image of this on the other side as well. And then I'm going to try and show you a visual of rotating this around. And it might look familiar to you as that bugle shape that we had before, although our limits of integration are going to be different here too. So we're going to do this using the shells method and utilizing this version of the theorem where we have two different ones, and come up with the volume of, in this case, this bugle shape. And then if we have time, we're going to go back and do this with, in this case, a disk method would work as well. But what we have here is we have two functions. We've got f on the top, which is f of x equals constant height of 4, and g of x underneath, which is the square root of x. And so that gets bigger the bigger x gets here. But I'm just going to give one particular cylindrical shell picture here, and so you can kind of see what that looks like here. So basically what we're doing is if we take that that scope that I was looking through and put it in on top, it's going to get caught in that bugle right on the top side. So what we really need to do is if we have our cylinder here, is we need to figure out the height here, right? And then we also need to figure out the base. So base times height. So basically we're going to end up getting this thing here, and our base times our height. Base is still going to be 2 pi times the radius, which the radius we're over here in our example at x. So it's still 2 pi x. So that didn't change. And if you notice, we still have the 2 pi x here. But as far as the height goes, what is this height? Well, the top function is f of x, and the bottom function is g of x. So basically this is going to be f of x minus g of x for whatever that x value is for that height. So basically we got to subtract away the one underneath, which is in this case the square root of x. So for us, f of x is 4 minus g of x is the square root of x. So it's 4 minus the square root of x is going to be the actual height here. So basically what we're going to be able to do now is take this antiderivative. So the volume will end up being 2 pi times the definite integral. Once again, we're going from a to b would be 0 to 16 in this case of x times f of x minus g of x is going to be 4 minus the square root of x. So this is 4 minus the square root of x, and then with respect to x. So remember, we're going out this way, that way, getting all that volume of that bugle-shaped thing in there. So anyway, so let's go ahead and do this. Let's multiply this out. This is going to be 4x minus x to the 1/2 times x is x to the 3/2 power. So that's what I have in there, and then take the antiderivative of that. So that's going to equal 2 pi times 4x squared divided by 2 is going to be that one, minus, and then x to the 3/2 plus 1 is x to the 5/2 divided by 5/2 is the same as times 2/5. I'm going to go ahead and do this all at once and plug from 0 to 16 in there. I can go ahead and simplify the 4 and the 2 and get 2x squared there. So anyway, this is going to be 2 pi times, when I plug in 16, I get 16 squared, which is 256, times 2 is 512. So this would be 512 minus, and then 2/5 times, when I plug in square root of 16 is 4 to the 5th power is 1,024, right? So times 1,024. And then, so that's the upper limit, and then minus the lower limit. Of course, if I plug in 0, I get 0, right? So, instead of doing that, I've just got that. Let me erase my little picture here. And then, if I simplify this, this would be 2 pi times the quantity 512 minus 2 times 1,024 is 2,048 And then what I can do is simplify, get a common denominator, etc. So I could do that. 5 times 512 is 2,560. So 2,560 minus 2,048 all over 5, and then times 2 pi, and doing that again. So subtracting that out, I'm going to get 512 times 2 is 1,024 pi over 5 cubic units. So anyway, that's what we get for our volume there. Once again, this is using the Shells method. We can actually do it the old way that we did on the way to the championship, right? In this case, if I did that, it would actually be a disc method, right? Because it would come like this. I'd be rotating that around there, and I would have my disc in there. I'd have the area of a circle. I'd go from 0 to 4. So if I did it with a disc method, it'd be pi times radius squared, right? However, I'd be doing it with respect to y. So if I did it with the disc method, let's do it that way and just see if we get something that works as well. So it's pi times radius squared. I'm going to do it vertically from 0 to 4. So once again, that's with respect to y. The radius then has to be in terms of y. So in this case, right here, I've got y equals the square root of x, but I need this as f of y quantity squared, right? So solving this for x equals y squared. So f of y quantity squared is y squared squared. That's y to the 4th power there. And this would be pi times y to the 5th over 5. Evaluated from 0 to 4. And if I do that, I get pi over 5. I'll keep that out front, and I'll just do the y to the 5th power is 4 to the 5th power. Once again, 1,024. And notice that that is 1,024 pi all over 5 cubic units, which is the same that we got doing it the Shells method with a top function minus the bottom function. And I know what you're thinking. So in this case, which one was easier? Well, using the disc method, going vertically, once again, it's not a washer because there's no hole in it, so that's a solid horizontal slice there. Adding it up vertically is a solid disc there. But anyway, so this one actually was a lot easier in this case to do it this way. So once again, if you have a choice, you can always try and use the method where you don't have to take one minus the other, outer minus inner, things like that. However, if you were told that you needed to do this using the Shells method, we could do that by just taking the top minus the bottom to figure out what that height actually is inside of there and utilize this theorem as well. So there's a couple more examples for you when the Shells method isn't quite so obvious.